Okay, hello everyone. In a new video, then we have reached part 2 of chapter 11, which is the chapter of mechanical waves for grade 8 students. Then now we have reached section number 5, which is the speed of the wave. The speed of the wave is given by so we know that the speed is denoted by v or vm. Then the speed of the wave is equal to v given by lambda, which is the wavelength, over the period t. So here, this is not the duration delta t, but the period of the wave, okay? So another formula for the speed or the velocity is given by lambda multiplied by f. So you can use either this formula or this formula depending on the given, and you should not forget that always the speed and forever can be calculated by Vm is equal to d over delta t. But here, since the speed is noted by v, so let me say that v is equal to d divided by delta t. So already we know this formula, and its triangle is given by, so here because we have divide, then v will be at the bottom, d at the top, and delta t here. As for this formula, here because we have multiply, then v will be at the top, lambda and f will be at the bottom. As for this one, here because we have divide, that v will be at the bottom, lambda at the top, and t here. And here let me recall what does each quantity represent, where v is the speed of the moving wave, and its unit is given by meters per second, which stands for meters per second. For sure here we are talking or discussing the SI unit. Okay. Now as for lambda, lambda is the wavelength, and its SI unit is given by m, which stands for meters. Capital T is the period, which is SI unit is given by s, which stands for seconds, and f is the frequency, and its SI unit is given by Hz, which stands for hertz. Okay. And as for the final formula, which is given by v is equal to d divided by delta t, so we are familiar with this formula from chapter 3. Now for that we are done with the chapter, the explanation of the chapter. Now we are going to solve exercises. Now let me start by exercise number 5, page 191. The title of this exercise is Characteristic of a Wave. In 5.1 we need to complete the following table. So the table consists of 2 columns, each column consists of 2 columns. Now as for the first column, we have the quantity, the name and its symbol. So we know that the symbol of the period is capital T. The symbol of the frequency is f, and the symbol of the wavelength is lambda. Now, for each of the following three rows, we need to give the name of the unit and its symbol. So the name of the unit is second, and its symbol is S. As for the frequency is hertz, and its symbol is given by Hz. As for the wavelength is given by meters, and its symbol is given by small m. Now as for 5.2, they are telling us what is the relation between the frequency and the period of a wave. Then previously we have discussed that the relation is given by the reciprocal. We have that the frequency is equal to the 1 of the period, or period is equal to 1 over the frequency. So this is the relation between them. Now in 5.3 they are telling us the frequency of a wave is 100 Hz, calculate its period. Then the frequency is given by 100 Hz. What about the frequency? Sorry, the period. The period is given by 1 over f. I'm using this formula, which is given by 1 over 100. Plugging this on the calculator, then the period is given by 0.01 seconds. So what does each one represent? The frequency represents the number of vibrations in 1 second. This period represents the time required to complete one vibration or one oscillation. In 5.4, they are telling us the period of a wave is given by 0.05 seconds. Then the period is equal to 0.05 seconds. We are asked to calculate the frequency. Then we always start by writing the proper formula, which is this one. So frequency is equal to the 1 over the period, which is 1 over 0.05. Now plugging this on the calculator, then the value of the frequency is given by 20. Because everything is expressed in the SI, so the SI unit of the frequency will be given by Hertz. Now as for 5.5, they are telling us a wave of frequency f is equal to 50 Hz. And propagates at the speed of, so let me change this and convert it to meters per second like this. And the speed is given by v is equal to 100 meters per second. And we are asked to calculate the wavelength. Then referring to the previous section, we know that the speed, the wavelength, and the frequency are related by this formula. V is equal to lambda f. Now constructing the triangle of this formula, here because we have multiply, then V will be at the top, lambda and f at the bottom. We are interested in determining the value of lambda, putting our hand over lambda, then lambda is given by V over f. The value of the speed in the SI is given by 100, and the value of the frequency is given by 50. So plugging this on the calculator, the value of lambda will be given by 2. Everything is expressed in the SI, so the value of lambda will be in the SI, which is meters. Then lambda is equal to 2 meters. Now in 5.6 they are telling us a wave has a period of 0.04 seconds. And the wavelength lambda is equal to 3 centimeters. Knowing that centimeters is not the SI unit of the wavelength, in order to convert from centimeters to meters, we divide by 100. So recall that from centimeters to meters, we divide by 100. This is equal to 0.03 meters. So we have the value of the wavelength and the value of the period. We are asked to calculate the frequency. So first of all, we know that the period and the frequency are the reciprocal because the frequency is 1 over the period. So frequency is 1 over the period, which is equal to 1 over 0.04. Plugging this on the calculator, Then the value of the frequency is given by 25. Since everything is expressed in the SI, so the SI unit of the frequency would be Hertz. So now we know the period, we know the frequency, and we know the wavelength lambda. We are also asked to calculate the propagation speed, which is simply the speed. So propagation is nothing but another word for motion. It is usually used for waves, and it's usually used for the motion of the wave and light. Now we need to calculate the speed. So if we refer to the formulas, here in this case we know the value of lambda, we know the value of the period, and we know the value of the frequency. We can use either this formula or this formula. I will choose this one because we have already used this, but you can use also this, for example, and you can check that the speed will be the same. Then V is equal to lambda over T, which stands for the period, then 0.03 divided by 0.04, plugging this on the calculator. Then the value of the speed is given by 0.75. Since everything is expressed in the SI, so the SI unit of the speed would be meters per second. Now let's move to the next exercise, which is exercise number 6, page 191. The title of this exercise is Fastest Wing Beat. Now the hummingbird can beat its wings up to 4,800 times per minute during a regular to and fro motion. Then during the regular motion, we have 4,800. So what does this number represent? The number of beats. But during 1 minute. So to and fro motion is nothing but an oscillation. This wing beat can reach the number of 12,000 per minute when plunging downwards. So during downward motion, the number of beats correspond to 12,000 beats corresponding to 1 minute. Now in 6.1 they are telling us calculate the frequency of a hummingbird's wing beats during a regular motion and during a downward plunge. So we need to calculate the frequency in each of the following cases. Now usually the frequency is calculated using the following formula: frequency is equal to the 1 over the period. But in this case we don't know the period during both motions. Now if we refer back to part 1 of this chapter, you can notice that we have stress on the fact that the period can be also, or the frequency can be calculated using the rule of 3. So whenever we have a correspondence between the number of vibrations and the time, we can determine the frequency using the rule of 3. But here you need to be careful that this time, which is considered to be here, must be in the SI in seconds. Now we have the following relations in each type of motion, but this minute must be converted to seconds. So let's start during the regular motion. And let me say that 4,800 beats corresponds to, but not 1 minute, however 60 seconds, because we know that 1 multiplied by 60 is 60. Now we need to calculate the frequency. If we refer back to the notes, instead of vibrations we will place F. Vibrations or beats, they are the same. So here we will place F, and now we'll crisscross, and this corresponds for 1 second. So in this case F is equal to so let me see. Okay, So 1 multiplied by 4800 divided by 60, this would be given by 80. And because everything is expressed in the SI, so the value of f will be in the SI, which is Hertz. And let me say that this is FR. R stands for regular motion. Then the frequency FR would be equal to 80 Hertz. Let me write here that during the regular motion, the frequency of the wings of the hummingbird is given by 80 Hertz. Now as for the downward motion, so we will repeat exactly the same steps. We know that each 12,000 beats corresponds to 1 minute. But instead of writing 1 minute, we will place here 60 seconds. And what about 1 second? It corresponds for the value of f, because the frequency is the number of beats or oscillations or vibration given in 1 second. Now if you cross multiply, then fd, d stands here for downward motion, is given by 12,000 multiplied by 1 divided by 60. Plugging this on the calculator, then the value is given by 200 Hertz. So Fd is equal to 200 Hertz. And as you can see, because the number of vibrations is greater, beats larger, then we expect that the frequency corresponding for larger or greater beats would be greater. Now let me make some space. Now in 6.2 they are telling us to deduce the period of the wing beats in each of these situations, and by deduce it means that we need to use the previous part. In the previous parts we have predetermined Fr and Fd corresponding for the regular and downward motion. No need to calculate the period using the rule of 3, but however the period can be calculated using the formula 1 over f, and by this we are using the previous part because we have already determined the value of f. Then let's start by the regular motion. Capital T corresponding for R, for the frequency, regular frequency, it would be given by 1 over 80. So 1 divided by 80 on the calculator, then the value of the period would be given by 0.0125 seconds. This is the period corresponding for 1 beat during the regular motion. So in order for the wings, in order for the wings to beat, so to move from point A, then to point B, then back to point C, during a regular motion, it takes an amount of time which is given by 0.0125 seconds. Now what about during the downward motion? The period, capital D, capital T, and subscript d for the downward motion is given by 1 over Fd, would be given by 1 over 200. Now plugging this on the calculator, the answer would be given by, just 1 second, 0.005 seconds. And as you can notice, the value of this period is smaller than this because the frequency is greater. So during a downward motion, the time required for the wings to beat from this point to point B, then back to A, is given by 0.005 seconds. Okay. So that's it for me in this video, guys. In the next part, we'll complete solving the exercises of this chapter.